Hello, welcome back to Learn Physics. In today's topic, we are going to continue with the system of particles and rotational motion. So here in this chapter, we learned till angular velocity and angular acceleration. So angular velocity is the rotational analog of linear velocity, and angular acceleration is the rotational analog of linear acceleration. Now we are going to study about the rotational analog of force. The rotational analog of force is called the torque acting on the system. What is meant by torque? Torque is represented by the letter tau. Tau is the representation for torque. Okay, torque is the rotational analog of force. So it is, say, if I am applying a force and which is constituting a rotation without translation, then we can say it is torque is acting on the system. See, suppose, while we are turning the pages of the book, see here I am taking a book and I am applying a force here, okay, which is helping to rotate. This is the rotational motion, isn't it? So here I am taking the book and turning the page. What is happening? See, I am applying a force in this upward direction. While applying the upward direction, what will happen? It is rotating about a fixed point. Okay, I am applying a force that is helping the object to rotate. Okay, so it is called as torque acting on the system. The force I am applying is helping the object to rotate. So while we are opening a window or a door, what is happening? That there also a force while we are applying over there. That force is helping the door to open, or it is helping the door to close with respect to a fixed, hinges are the fixed point, isn't it? So if I need to see, usually while we are turning the page or while we are opening the door or windows, what will happen? We will be, see, in the last end only we will be touching it to open, or we won't be choosing a point which is near to the hinges, isn't it? While I am turning the pages of the book, I won't turn like this. This end only I will take, isn't it? If we are trying to open the page from here, I should apply more force on it, isn't it? I should apply more. So the amount of torque acting on the system depends on the distance from the hinges, from the fixed point. Okay, so with respect to a fixed point, if the distance is more, then the torque acting on the system will be more, because if the same force if I am applying, torque will be more if we are choosing a point which is away from the fixed axis. This fixed axis is the axis of rotation. This hinges will be the axis of rotation. Okay, clear? So it depends on this distance from the axis of rotation. Here I am considering a coordinate system. This is x-axis, this is y-axis and z-axis. This is the origin O. I am considering a point P here. With respect to the origin, it is at a distance r. R is the position vector. Along z-axis, I am applying a force F here. Okay, so the angle between R and F is theta. Okay, theta is the angle between R and F. Then how we can find out the torque acting on the system? See, I will be considering the force is acting in this direction, isn't it? In this direction force is applying. I am taking the perpendicular component, which is the distance which is perpendicular to this force. This should be 90 degree. So what will be this distance? This will be r sin theta. Okay, this component is r sin theta, and so torque acting on the system, which will be acting in this direction perpendicular to both r and f. Torque will be acting perpendicular to both r and f. Rf sine theta, or we can write it as it is equal to r cross f. Okay, clear? This is how we will be finding out the torque acting on the system, and it is otherwise called as the moment of force acting on the system is called as torque. So torque definition is moment of force acting on the system is called a torque, and the graphical representation for torque acting on the system will be this one. This r sine theta, which is perpendicular to f. So we are considering it is the product of force and the perpendicular component of the distance from the fixed axis. From the axis, what is the fixed, how much distance is acting perpendicular to the force? It's not like we are, see here, while we are considering, we will always apply a perpendicular force, isn't it? So if we are not applying a perpendicular force also, the component which is acting perpendicular to the force only will be helping it for this torque acting on the system. So it is otherwise defined as it is the moment of force acting on the system. Okay, so here this is torque, which is a rotational analog of force acting on the system. Okay, now so we learned about the torque, and so rotational analog of force we learned acceleration and velocity. Now momentum. What is the rotational analog of momentum? Rotational analog of momentum is called as angular momentum. Rotational analog of momentum is called as angular momentum, which is represented as L. L is the rotational analog of momentum, that is angular moment of linear momentum. How we can define angular momentum? It is the moment of linear momentum. Linear momentum. So linear momentum we know it is P, isn't it? So L is equal to R cross P. This is the definition for others angular momentum. Angular momentum is the rotational analog of linear momentum. It is called as moment of linear momentum. L equals R cross P. All these are vector quantities. We know cross product is a vector product. So it is angular momentum. Clear this? So now we are going to study a relation between torque and angular momentum. Okay. So the next one is the relation connecting torque and angular momentum. What is the relation connecting torque? Torque is the moment of force and angular momentum is the moment of linear momentum. So first I am considering torque acting on the system. What will be the torque acting on the system? We already learned it as torque tau equals R cross F, isn't it? So, and L equals R cross P. Okay, these two terms just now we learned, isn't it? Now I am going to consider dl by dt, differential of L with respect to t. So I can differentiate both the sides d by dt of R cross P. Okay, now R differential of a cross product, how it will be? First function into differential of second plus second function into differential of first. First one, first function into differential of second plus second function into differential of first, that is dr by dt cross P. Okay, here first I am considering dr by dt cross P. I can write it as m into v, isn't it? dr by dt cross mv. So m is a constant, I am taking it outside, and dr by dt is v cross v. What is v cross v? Sine 0, 0, because v and v, the angle between v and v will be 0. Sine 0, 0 it will be. A cross B, A, B sine theta. Theta is 0, so sine 0, 0. So this term will become equal to 0. That is dr by dt will become equal to 0. So which is existing here? dl by dt equals r cross dp by dt. What is dp by dt? As per Newton's second law, we know that dp by dt is F. What is R cross F? It is torque. So we are getting a relation like tau equals, what is tau? dl by dt. This is the relation connecting torque and angular momentum. Clear? Torque tau equals dl by dt. Okay, easy calculations, right? Now this torque and angular momentum, we learned it for a single particle. If we are considering it for a system of particles, what will happen to the torque and angular momentum? See here, first I am considering the torque acting on a system of particles. So while we are considering a rigid body, it has many number of particles, infinite number of particles will be there, isn't it? So all these particles, while we are considering, what will be the torque acting on the system? See, one single particle while I am considering, I can write it as torque equals R cross F. So, but a system of particle, while I am considering, I am giving an external force. Because of that, an external torque will be developed in the system. Okay, that is there. What about the internal torque which is acting between the particles? So, while they have an internal torque between the particles, there are many number of particles, isn't it? So, one particle will be acting a force on another particle, and another particle will be acting a same and equal and opposite force in the opposite direction. So total, while we are considering, what will happen? The net force will become equal to 0. Okay, net torque acting on the system will be equal to 0. It will be acting along the same line. It will be opposite in direction. So the net torque, internal torque acting on the system will be equal to 0. Tau internal will be equal to 0. Only external torque will be acting on the system. So this external torque, how we can find out? Tau 1 plus tau 2 plus etc. plus tau n, like that. N, if n number of particles are there, means we can consider till tau n. N number of particles are there, we will be considering this external torque. All the points we will be adding up, and together we will be finding out the torque acting on the system. Okay, clear? So here, and now we got the value of a relation connecting torque and angular momentum. Tau equals dl by dt, and any analog you can remember from our translational motion. Yes, then Newton's second law, F is equal to dp by dt was there, isn't it? So here it is tau equals dl by dt. So those terms only you should remember. Okay, torque tau equals dl by dt. So after F is equal to dp by dt, there what we learned? Conservation of linear momentum. Okay, so here we are going to study about the conservation of angular momentum. What is conservation of angular momentum? So how we can find out the conservation of angular momentum? If, see, tau equals dl by dt. If torque is equal to 0, if the torque acting on the system is equal to 0, then dl by dt will be equal to 0. When the differential of a quantity will be equal to 0, when that quantity is a constant. When L is equal to a constant, then dl by dt will be equal to 0. So if you are writing this as a sentence, you will get the answer. If the net torque acting on the system is 0, that means if there is no torque acting on the system, then the angular momentum will be remaining constant. Angular momentum of the particles remains constant in an isolated system. So while we are considering an isolated system, if no torque acting on the system, then the total angular momentum remains constant. This is called as conservation of angular momentum. Conservation means it will be remaining constant. Always energy conservation means energy will remain constant. So here in the conservation of angular momentum, if there is no torque acting on the system, then the angular momentum remains constant. Okay, so this is conservation of angular momentum. Clear? So next we are going to study about the equilibrium of a rigid body. So next is equilibrium of a rigid body. So when the equilibrium, it will be in equilibrium means net force acting on the system should be equal to 0. That is the equilibrium condition which we learned in our translational motion. So here how it will be, how the equilibrium will happen for a rigid body. See, if the obviously force acting on the system is equal to 0, if the net force acting on the system is equal to 0, then the object will be in translational equilibrium. So for a rigid body, which and all type of motion can it be possible for a rigid body? It is rotational as well as translational motion is possible for a rigid body, isn't it? So here in the case of rigid body, we should consider about the translational motion as well as the rotational motion. That is, in translational motion we can say if the net force acting on the system is equal to 0, if the net force is equal to 0, algebraic sum of all the forces acting on the system is equal to 0, then we can say the object will be, the rigid body will be in translational equilibrium. And in the case of rotational motion, if the net torque acting on the system is equal to 0, if the net torque acting on the system is equal to 0, then the object will be in, the system will be in rotational equilibrium. So if both the conditions are obeying, then only we can say the rigid body will be in equilibrium condition. Okay, so net force is equal to 0 or net torque acting on the system is equal to 0, then we can say the rigid body will be in equilibrium condition. So net force, how we can write down as an equation? Sigma I equals 1 to n Fi is equal to 0. That is F1 plus F2 plus F3 plus etc. plus Fn, that is equal to 0. So here if we are writing it an equation, sigma I equals 1 to n, tau I equals 0, tau I is equal to 0, then we can say this object will be in rotational equilibrium. So if both the conditions it is obeying in a rigid body, then we can say the rigid body is in rotational equilibrium, or the rigid body is in equilibrium. If the net force acting on the system is equal to 0 and if the net torque acting on the system is equal to 0, then we can say the object will be in equilibrium. That rigid body will be in equilibrium, we will say. Okay, clear? So next is, see here, this is a pen. In this pen, if I want to open the cap, how I will be opening? See, I will be opening it like this. So this here, I am using these two fingers and one finger is applying a force here. In which direction if it is acting? See, I will be applying a force in this direction and with the thumb I will be applying a force in the opposite direction. Okay, so two equal and opposite forces I am applying. See, if I am considering like this, see here this is rotational motion. I am trying to open this, isn't it? So first it is rotational motion. If I want to rotate like this, rotational motion means with respect to a particular axis, one force is acting in this direction, in this direction, and another force is acting in the opposite direction, isn't it? So two equal and opposite forces which are separated by a distance, so which has different lines of action. So one force is acting in this direction and another force is acting in this. The same kind of another force is acting in the opposite direction, which has different lines of action. This is the lines of action here. This is the lines of action with the different lines of action. So this is called as, this two forces are called as a pair of forces which have different lines of action is called as coupled. See, if I am considering a rod like this is a rod AB and which is fixed at the point C. Okay, I am applying a force A in this direction and I am applying another force in this direction. So what will be the rotational effect over here? It will be acting in this direction and this will be acting in the opposite direction. Then what will be the torque acting on the system? Yes, equal and opposite forces. It's not equal and opposite. These are equal and in the same direction. So what will be the rotational effect? This one, and this is acting in the opposite direction. So the net force acting on the system will be equal to 0. About a fixed point, two forces are acting in the same direction. So net force is equal to, see here net force I am considering, that is not equal to 0. But net torque acting on the system will be equal to 0 because no rotation will happen, it will cancel. So instead of that, if I am considering a rod AB which is fixed over here, one force is acting in this direction and another force is acting in this direction. You tell me what will be the rotational effect? Rotation will happen like this. If I am applying over here, rotation will happen like this. So which is causing a rotational effect. Seesaw. That is what happening in the case of seesaw, isn't it? So if one force is acting in it, other will be moving up. That is rotational effect. Okay, so that is this one causes a couple. Okay, a couple will be producing because of this. Okay, so understood all these things. So what is meant by a couple? Two equal and opposite forces which have different lines of action. That is called as couple or torque acting on the system. So couple will be producing translational forces not there. The total force acting on the system is not equal to 0 here in this case. But the torque acting on the system will be equal to 0. But if the total force acting on the system is equal to 0, then about a fixed point, then it will be having a rotational effect. Okay, so that is what happening in the case of rotational motion. Okay, clear? So this is about the couple. So in today's topic we learned about the torque acting on the system, angular momentum, conservation of angular momentum and couple. Okay, so it will be causing a rotational effect only if it has different lines of action. That is very important. If it has different lines of action, then it will be causing a rotational effect. That is what in the case of opening the cap and in a magnetic field also. See, in Earth's magnetism, while we are considering, see, north, south. See, this is north pole and this is south pole. It will be rotating like this. What is the reason? Two equal and opposite forces which is acting in the opposite direction, isn't it? So that will be causing a couple. Because of that couple only, this rotation also happening in the case of magnetic needle. Okay, Earth's magnetism, while we are considering north-south pole. So rotation is happening because of this forces, magnetic forces. Clear? So I hope all of you understood all those things. If you like the channel, please don't forget to subscribe and support me. Okay. Thank you for watching. Bye.